So may I ask you for attention again? So we are going to the second part of Amanda's talk. We have been asked if we will provide the slides of the presenters. Of course, you will get a list of all presentations which are going to be presented here. We are also recording the presentation, so in case the quality of the record will be sufficient and if the presenters will allow to do that, we will also give you the record of the presentations. But it doesn't mean that you don't have to attend the lectures. So. I don't know, even this? Okay, so you can plug in your computer. Behind you there is possibility to recharge your mobile phones and computers. Yeah, so hopefully this is everything from the organization point of view. And Amanda, you can use 1 hour, 1.5 hours, so the lunch can be a bit delayed, of course.
Okay, super. Thank you very much, Martin. Okay, so in my second lecture, what I want to talk about is actually task assignment and task allocation in multi-robot systems. Again, like in the previous lecture, I'd like to start off by giving you a very brief introduction to task allocation by giving you a motivation that stems from nature. And then I will be going through a couple of classical assignment algorithms. So I'll be talking about the Hungarian assignment algorithm. I'll be talking about swarm distribution methods. And I'll also talk about market-based and threshold-based assignment mechanisms. So where does the motivation for task allocation and task assignment actually come from? So in nature, actually, task assignment and task allocation is one of the most fundamental concepts of organizing colonies of social animals. So for example, for this ant species, they actually grow into two different castes as they evolve. And these two castes, they actually work together. And you can see how, so these researchers, they actually observed the activities of this ant colony, and they were able to show that this smaller ant here is involved exclusively in very minor tasks, such as cleaning and carrying around the eggs, or for example, laying or distributing food inside the nests. So some very kind of mechanistic tasks, whereas the larger ants in this ant colony they were involved in self-grooming, which is arguably a very important thing to do, but they were especially involved in the guard nest entrance guarding. So this is arguably a very important activity to be involved in, because if that fails, then the whole colony is put at risk. So they specialize the tasks of these ants, in this particular case, to correspond to their physical morphologies. Another way of viewing task allocation, task assignment in natural systems is through temporal assignment. So in another organism species here, some biologists actually found out that there's this concept called temporal polytheism, where they saw that younger bees were involved in tasks such as cleaning, tending to the brood, tending to the queen, eating pollen, etc. And as the bees grew to become more mature members of these bee swarms, they started doing more important things such as patrolling and also resting. So you can see how this task assignment in nature not only corresponds to, say, the physical morphology of the actual animals, but also perhaps maturity, so things and skills that they learn to do as time evolves within the organism's lifespan. And one of the main reasons that they do this is because nature have found out that doing specialization allows them to, or doing task assignment and task allocation in colonies allows the animals to specialize to these roles and still to work together. And this led to a higher fitness of the colonies and then also contributed to the overall reproductive mechanisms and the survival of these colonies in nature. So this idea of task allocation and division of labor is something that you'll find again and again in very many different kinds of species. So taking some of this motivation out from nature back into the engineering domain, we can look at the various kind of problems that we're interested in solving, and we can think about how task allocation or task assignment actually solves something incredibly fundamental for us in the multi-robot systems domain, because it answers the question of which robot should go where and which robot should do what. And you want to be very careful about this decision because it'll define the performance of your overall mechanism. So, for example, we can think of task assignment simply in the warehouse and product delivery problem, where you're sending specific types of, or specific individuals in your robot team to get specific crates of products. You can think of task assignment in the mobility on demand systems, where the assignment is maybe based on vicinity, but potentially also on the capacity of the vehicles. You can think of situational awareness or even monitoring, where you could be thinking of different vehicles with different sensing capabilities, or also proximity, where that plays a role. So here an example for monitoring and surveillance. There the question is, well, where do you assign the respective, which areas in space do respective robots end up being assigned to? Maybe you're trying to minimize the time it takes for these robots to reach these individual cells. In the area of more general task assignment, you want to be assigning robots to tasks that correspond to their specific tools, to the actuators that they have, or maybe the sensors that they have, in order to be able to guarantee that you actually can solve individual tasks, where the tasks are not necessarily homogeneous, so they can be different types of tasks. And again, as I already mentioned, in the case of mobility on demand, you're going to be assigning robots to humans based on potentially where the vehicles are, or where the humans are, and how many how many humans you're aiming to pick up and transport. So this is a video from Kumar's lab at Penn, where it's actually showing us how the task assignment or task allocation problem also transfers to mobility problems. And what they're doing here is actually, so they also have a higher order optimization objective, which is essentially saying, I want to assign robots to new locations in space so that I don't have collisions, and so that I'm minimizing the time for these transitions to take place. So this is also a task assignment problem, because again, we just have an optimization objective that we're trying to achieve, and we have a couple of underlying constraints that we also want to satisfy. And so this is another beautiful example of how task assignment is very fundamental to everything that we do in multi-robot systems. So what is task assignment? So the problem statement says it's going to, if we solve the task assignment problem, it's going to tell us which robot should go where and which robot should do what. And then the key question which remains to be answered is, well, what is a task in this case? And there are many different ways that we can think of tasks. So we can think of discrete tasks, where we can say, well, a robot can go and pick up a parcel. This is a discrete event that needs to happen. A robot should go from A to B. Or it could be a continuous event, where we're saying, well, we have this area here that needs to be monitored continuously, and we need a robot or some robots to be doing that throughout time without interruption. The key assumption that we're making here when we talk about task assignment is that we don't have scheduling, so temporal constraints, because if we do, the problem becomes a different problem, which is then called scheduling. And I will not be talking about scheduling today, because task assignment is already a rich enough problem. But this is also something very important to think about, especially when solving different tasks have time dependencies. So you might need to solve task A before task B can be started. So also a very important type of problem to think about. So the assignment method, so it's actually something that is a problem that many people have already thought about in research, and it goes way back. And we can think of assignment stemming from perhaps most originally operations research, where researchers were thinking about logistics primarily. And this relates to the whole field of economics, perhaps also scheduling. But some researchers have looked at the task assignment problem in the area of network flows, so a little bit more in the continuous domain, but also the assignment of packets to routes, for example. And the general method that solves, at least for us in the discrete domain, is combinatorial optimization. So that's one thing that you have to feel very comfortable with if you want to think about how to solve task assignment problems. And one of the most classical ways of actually formulating a task assignment problem is by modeling it as a bipartite graph and solving a bipartite graph matching problem. So how do we think about this in the sense of multi-robot systems? So first thing you need to define is what you want to optimize. And you can think of this in two different ways. So either you have a utility that you want to maximize, or you have a cost that you want to minimize. So those are the two options that you have. This cost or the utility will depend on your context, clearly, where in this particular case, we're going to assume that we can obtain knowledge of the utility. And of course, if we have perfect knowledge of what the utility is for any given assignment, then we can solve the assignment task optimally. So we can formulate the problem as I demonstrated in this little example here. For here, I'm considering a utility of assigning a robot R to a task T, where we could, for example, arbitrarily say the utility is equal to Q, which is the quality of the task being solved, minus C, which is the cost of actually doing that task, if the robot is actually capable of solving that task, and 0 otherwise, right? So this would be a very simple way of quantifying what utility means to us in a task assignment problem. And so here in this little drawing here, I have the utility of robot 1 doing the task 1 being 1, and the utility of robot 2, sorry, no, this is just the graph notation. So U11 would be quantifying robot 1 being assigned to task 1, and U21 would be the utility of assigning robot 2 to task 1. So then we can take this a step further and say that we want to, for example, maximize the performance of our robot system, where we define one utility metric, which is this equation here, which is a sum over all robots and a sum over all tasks, where the important bit here is this variable xij, which is essentially an element of an assignment matrix, which would then be, say, capital X. And xij is nothing more than a binary variable, which basically says, well, if it's a 1, then I'm assigning robot I to task j, and if it's a 0, I'm not assigning robot I to task j. And then I have constraints on these variables xij, because I can only assign one given robot to one given task, because a robot can only do one thing. And I'm only going to assign one robot to any given task, so I don't need more than one robot working on any given task. So those are the two constraints that I have in my system, and if I can then maximize this objective subject to these two constraints, then I solved my task assignment problem optimally. And this is just a representation of what this might look like. So on one hand, so this is the bipartite graph representation, where on the one hand side, I have all my robots. On the other hand side, I have all my tasks. It's a complete graph because in this particular case, I can assign any robot to any given task, and all I have to do is find the best matching that maximizes my objective. So how do I do that? So the classical go-to algorithm that solves this optimal bipartite graph matching problem is called the Hungarian algorithm. It was published by Kuhn in 1955 based on earlier works of two Hungarian mathematicians, Koenig and Egerváry. And basically what Kuhn did is he summarized this algorithm into 4 key steps, which are very simple and are operators essentially on a given assignment matrix. So the recipe is here, and we're actually going to go through an example on the next slide, where the key steps are basically working on the rows of your matrix, analyzing the rows with respect to the zeros that you're producing, and manipulating the numbers that you have in your matrix in order to solve the task assignment problem until you know that every robot has been, or every task has been assigned one robot or one agent. So what does this recipe actually boil down to? So in this particular example here, I've constructed a task assignment matrix where the cells here correspond to, let's see, I think I'm trying to minimize the cost. So this is, the variables here are costs, so I want to minimize the sum over all the robot to task assignments. And so what I'm going to start by doing is saying, okay, I'm going to subtract the row minima from all the rows in this matrix at step 1. So I'm going to subtract from row 1, I'm going to subtract the minima, which is 69. From row 2, I'm going to subtract 37, etc. And that's going to produce, and I do the same for the columns in step 2. And then at step 3, that's going to produce me a new matrix, which has a couple of zeros. So at that point in time, you're going to find the minimum number of rows and columns that cover all of the zeros in my resulting matrix. In this particular example, I have 3. Which means that not all my tasks are satisfied at this point. So given that I still have a task that is not serviced, I have to go back and perform an additional step, which is a step number 4, which basically tells me to find the smallest uncovered element from the preceding matrix that I had before. And I'm going to subtract it from my unmarked elements, and I'm going to add it to my twice marked elements to produce a new matrix, which is that matrix just there to the right. And then I'm going to move back to the same step that I did at step 3, which is try to cover this new resulting matrix again with the minimum number of rows or columns that I can find to see if I can find, in this particular case, 4 rows or columns that cover all of my elements. And in this case, I can now find 4 lines that cover my whole matrix, which means that my task assignment algorithm is satisfied. And so in the last one, you can actually find what robot is actually assigned to which task, and that corresponds to the elements where I have my zeros. So for example, robot 1 would then be assigned to task 3. And by summing the costs, which I have represented in step 0, we can then assert that this is indeed the minimum cost that can be found for this particular cost matrix. And so this is how the Hungarian algorithm works. And it has a computational complexity of n to the power of 3, where n is the number of tasks or agents in my system. So how would I actually apply this Hungarian algorithm to a real-world problem? So one example one can think of, and I hope you can see this roughly. So here I have an example which is stemming from the mobility on demand literature, where we're trying to infer what vehicle is going to be assigned to what passenger in my system. And the cost in this particular case is simply going to be the travel time, because we want to minimize the overall waiting time for all the passengers in my system for a given assignment batch. So say I'm collecting over 10 seconds, in a 10-second time window, I'm collecting all the passengers that need to be serviced. I have their locations. I know where my current batch of vehicles is. And then I just find the assignment that minimizes this particular cost. And I then send the vehicles to pick up those passengers. So this is a very simple way of how a system such as Uber or Lyft could function. And actually, so some of my work actually implements a system along those lines. And you can actually do this by saying, well, I'm going to take a geographical area, I'm going to represent that as a map, and I can infer the travel time from between any 2 vertices in my underlying map based on quantitative data that allows me to estimate the average travel time between any 2 nodes, so on the edges of my graph. And then that allows me to compute things such as the cost of traveling between any 2 nodes in this graph. So again, you can see how using graphs as an underlying representation here is very useful to solve this kind of problem. And so this is the optimization that we're actually trying to solve here. Aij are the zeros and ones that I'm trying to infer, and Cij is the matrix of all the costs, which is built dynamically at every assignment batch when your passenger requests come into your system. So actually a very simple algorithm that can solve these otherwise relatively complex problems. So a couple of things about the Hungarian algorithm. So the Hungarian algorithm actually makes a lot of assumptions. So first of all, it's assuming that the costs, the utilities, are known at a centralized computational unit. So somebody knows exactly what time, how much time it'll take for any car to reach any passenger, for example. We assume that the costs are deterministic, so they're going to, once this estimate of the cost is made, it's not going to change, and it's not random either, so no stochasticity. The costs are constant, so no dynamics. And we're also assuming that we have one-to-one assignments. So one robot is going to service one passenger in the system. So those are the basic assumptions that we're making here. The complications are, as soon as we move to real-world systems, are actually quite numerous. So first of all, there is uncertainty around utility and cost. So transport is actually an excellent example because the travel time that we're estimating for a vehicle to reach any passenger is certainly not constant. It's definitely stochastic. So things can happen, roads can be blocked, traffic accidents happen. There are also minor things that can happen to the driver whilst he's driving, or if it's an autonomous car, perhaps there are perception failures. So there's a lot of random things that can happen that can have an impact on how long it might take a vehicle to get to a certain location. So this isn't the case of travel time, but other ideas along those lines also apply to more general assignment problems where simply the utility is not well defined or not well known a priori. Dynamic environments can change utilities and costs. So if you think about search and rescue, you don't know the conditions that the robots are going through as they try to reach their tasks, and you don't know necessarily how useful the robots will be once they get to their tasks. So these are things that might be very difficult to model and to know or to predict a priori before your robots actually get to the task and are actually already doing them. So solving these assignment things a priori is not trivial. And finally, when you have heterogeneity in tasks and heterogeneity in the robots, sometimes you have interdependencies between tasks and robots, or between tasks and robots that make the whole assignment problem combinatorially much more complicated. So the consequences of all of this is that, well, we can kind of sweep these assumptions under the rug and still try to solve the problems with the Hungarian assignment algorithm, but the resulting performance will certainly be suboptimal. And if we try to not sweep these assumptions under the rug and try to take them into account, the problem that we run into is that they become NP hard to solve for a number of reasons. And hence, we really end up in the situation where a lot of the problems that we're actually really interested in solving become practically infeasible. And this is where research becomes really interesting, because then we're there as multi-robot systems scientists, we're trying to model the utilities and model the costs in such a way that we can somehow make these problems practical to solve in real time nevertheless. And that's where a lot of the focus has been, at least in this domain of multi-robot systems research. So I'm going to talk about a couple of these things in this lecture. So in this particular example here, we can think of the problem where some tasks actually might require more than one robot in order to be solved. So what does that mean for our assignment problem? What this actually means is that, well, if I want to try to find what group of robots can solve a task optimally, what I have to do is I have to evaluate all the possible groups that I can put my robots into in order to define what the utility is of any given group for any given task in my problem. So what does this problem statement look like formally? So formally, what I'm saying here is I'm trying to analyze how many different ways I can partition a system of n robots into k non-empty subsets, right? And so it's been shown that the number of these possible groups is given by the Stirling number of the second kind. And just to give you an intuition of how big this number is, if I have 10 robots and 5 tasks, that's already more than 42,000 different possible groupings that I can create. So if I have 10 robots and 5 tasks and I want to find out what is the best grouping that I want to create for my robots, I have to evaluate more than 42,000 possible assignments before I know which one is the best one. And so here the problem starts becoming interesting, because this becomes intractable if I'm trying to do these things really quickly in real time. So, okay, so let's formalize this problem and let's think about how we can solve this. So here we're looking at the problem of forming robot coalitions, where formally we can say, okay, we have a ground set E, which consists of all the robots, and X is going to be a family of subsets. And we know that we need all the robot subsets to be mutually disjoint, so no one robot can be part of 2 subsets simultaneously. And we also know that the union of all subsets is equivalent to the ground set, so we want all our robots to be utilized. Then we say that we have what I'm calling, or what is known as, the set partitioning problem, which says, well, we have, assuming we have a finite set E, a family F of acceptable subsets of E, and a utility function that says what the utility is of assigning a given subset to a given task. This is mapping onto the scalar domain. What I want to do is find a maximum utility family X of elements in F such that X is a partition of E, okay? So this is the formal definition of the set partitioning problem. And it has been shown formally that the set partitioning problem is strongly NP-hard to solve. So there are a number of ways we can think of trying to solve this problem, and I have a couple of references at the end of my presentation that give you a couple of ideas. But one thing I want to talk about today, because it's an interesting way of actually tackling the problem, is by saying, well, we'll actually try to relax the problem into the continuous domain instead of trying to solve it in the discrete domain. So this is a creative approach, an interesting way of doing it. And just before I talk about that, I want to spend a few seconds actually talking about why or how and when we can actually do this kind of transition from the discrete to the continuous domain. So what I'm essentially implying is that I'm making a transition from countable discrete systems to uncountable systems. And fundamentally, this actually brings up the more philosophical question of, well, what is the difference between a multi-robot system and a robot swarm? And actually, when I go to conferences and meetings, a lot of people actually come to me and ask me this very question. So when I talk about very large multi-robot systems, how many robots is a swarm? And my answer is actually, well, it's not in the number of robots that you're using, but it's actually in the method that you're using. So if you're using a control method that is assigning a specific robot that you can count, that potentially has an ID, to a specific location or task, then this is a multi-robot system to me, which is solved by methods that stem from the discrete domain, and all the robots are countable. However, if I'm saying that I have a swarm of robots where I don't necessarily count about the IDs, which are potentially homogeneous, and I'm using methods from the continuous domain, so continuous control methodologies, then I have a robot swarm. So that's my way of viewing it. And so what I'm going to do today is present you a method of doing or solving the task allocation problem for robot swarms. Now, clearly, you can't use these methods for all applications. So Ocado, which is, for those of you who know how the UK does grocery deliveries, it's very similar to Amazon, where they do these assignments of robots to groceries in their warehouses that have rails on them. This is clearly a countable problem and definitely cannot be solved by swarm technologies. But there are some areas where you can think of, well, maybe you want to monitor an environmental area, you want to have a certain amount of sensing happening in certain areas, and you don't necessarily care about if there are just 3 or 4 or 10 or 15 robots there, but you care more about the qualitative effect of a team of robots. Then potentially that is a good application for methods that stem from the swarm domain. Okay, so very important to distinguish these two classes of problems, and clearly the countable problems have to be addressed by discrete methods that normally stem from the combinatorial approach, and swarm type problems can leverage different types of control methods that make mean field assumptions. So the nice thing is that moving to the continuous domain might be approximative or only has guarantees on average, but some of these methods, if they're implemented in an efficient and elegant way, are extremely fast and extremely effective. So I'm going to show to you how this can be done. So what we're going to do here is we're going to consider that we have 5 locations in space, and we're going to imagine that this here is a geographical monitoring problem where I need to have robots survey these different buildings, and I need to have them go around these buildings continuously to provide information about what's happening there. And as time goes on, maybe the requirements of surveillance, they change around these buildings, and I need to deploy robots of different types to these various buildings in my area in order to get the right sensing information or contextual information that I need in this space. So that's kind of the problem layout here. So what I'm going to do is I'm going to say I have different robots here with different capabilities, and I'm going to formalize the problem as being represented by a set of tasks where the robots can move along the edges of this underlying graph representation here, this road network, in order to move from one task to another. And I'm going to make another assumption here, which is going to be saying, okay, since I'm in the continuous domain, I need to quantify what proportion of capabilities or what proportion of robots of any kind I need at any one given task in this network of tasks. So say that the blue bar here means I need X amount of video streaming happening in this area, and I need to or so much resolution of the specific area, and as a function of that, tell me how many robots roughly I need to deploy to that area in order to make this happen. So this could be one way of interpreting this. So if I can somehow represent my model formally in this way, then what I'm going to do is I'm going to implement a redistribution scheme that applies to robot swarms. So here what I'm going to say is X is going to represent the distribution for one specific robot type amongst these 5 tasks in my robot, in my task system. And what's important here is, since I'm making this mean field approach, I'm thinking of proportions, right? So the sum overall, these values here in my X vector is 1. So I have 100% of the robots of this particular type, they're distributed, right? So what I then am going to do is I'm going to say, well, I'm going to formulate a dynamical systems problem that tells me how the proportion of my robot or how the distribution of my robot system changes as a function of time. And I'm going to say that this changes in a proportional way, where K is essentially my gain matrix, and X is the current distribution of my robots over all these tasks in my system. So a very simple and classical way of representing this control problem. So this matrix K, if we look at it under the hood, what it's telling me is, well, it's composed of these matrix elements Kij, where I is one given task and J is another given task. And Kij is essentially telling me the transition rate for that robot type to move from one task to another. Okay? So by multiplying my current robot state by this transition matrix, I will understand, or I will be able to model how my robot swarm evolves over time. And so I need to now solve this problem because I want to find out what my x of t is, right? And I can do this simply by taking the matrix exponential of my transition rate matrix k. If I multiply e to the power of k by x0, which is my distribution of my robot swarm at t equals 0, so at its origin, then I can find out so I have e to the power of k times t. Then I can find out what the distribution is of my robot swarm at any time t. And this is all there is to it, really. So this is the solution of my system. And now that I know how to represent the solution of my system, all I need to do is to say, or to find a way of formalizing an optimization objective, which in this particular case would be saying that I have a desired robot distribution x star, and I'm going to try to solve the redistribution of this robot team so that I can find a k star that achieves my x star as quickly as possible, right? So I can formulate an optimization problem that satisfies these 2 constraints, and then I can think of different ways of actually solving this optimization problem in order to achieve these goals. So to achieve my robot distribution as a function of what I'm desiring, and to do it so that the robots reach their goals as quickly as possible. And so here are just a few references that go into more depth of different ways that you can actually solve these kinds of optimization problems. So now I told you how to find transition rate matrices, but what does this actually mean for us? Well, what it means for us is that once I have this transition rate matrix, I can actually synthesize a controller for any individual robot that is part of this swarm. Because what it essentially means is that, well, I have this matrix K from which I can extract the rates for task-to-task transitions. So essentially, if a robot knows the rate Kij for its particular robot type, then all it has to do is, once it's at a task, is to throw a random dice and infer if it should move to the next task or not, because it's essentially a controller that abides by these probabilistic transition laws, right? And the result of this is that, in average, I will achieve this desired redistribution of my robots with an extremely simple control law that can be computed extremely quickly. Okay? So I want to show you a little movie that actually demonstrates this system working. So this particular movie actually stems from a paper that we wrote that solves a slightly different and a slightly harder problem, which I don't go into details here, but I just want to explain to you what's happening here under the hood. So you can see on the top right-hand corner, I have 4 different robot types, where each robot type has a combination of capabilities that are here represented through these different colors. So species 0 here has capability pink, cyan, and green. And what I have at these disks here is tasks. So each of the disks here is a task in space. And these wireframes here represent how much of a certain capability I need to have present at any one of these tasks in the system. So the thing that makes this problem combinatorially extremely difficult, if I would try to solve this in the discrete domain, is that my different robot types, they have overlapping capabilities, which is very difficult to solve if I were to be applying methods from the countable approach, so in the discrete domain. But by relaxing it into the continuous domain, I can use what I described to you previously, and I can solve this for optimal transition rates for these interdependent robots in the system. So this is the initial distribution of my robots, and you can see how, as my individual agents, they move underneath these disks, they're essentially carrying in their capabilities into the task area, and you can see how, as time progresses, the amount of capabilities converges to the required amount, so the wireframes are being filled up slowly. And as time goes to infinity, you'll see that the fluctuation will be around these desired amounts, which is the average, the exact average that we're achieving, that we're aiming to achieve in the system. So this shows you what we could do if we would employ continuous methods to solve problems that we can formulate within the swarm framework. And just to show you that it doesn't necessarily have to be for very, very large systems, so here I have hundreds of robots, but we can also do it for robot teams with very few robots. So in this particular case, at the time, we implemented a system or a small swarm of robots with just 5 robots, where I only had 2 different robot types. So I had species 1, which are these red boats here, and I had species 2, which is that one blue boat over there. And instead of using a method from the discrete domain, we're using the exact same swarm methodology to achieve these probabilistic transition rates. And as I play out this movie, let's see. Yep. Hopefully. Oh, was it starting? Oops. Okay. Patience. Yeah, I think now it'll start. So here you can see, so the tracks there, and on the top right side panel, you see how the error decreases over time. And these boats, they're essentially applying this probabilistic controller, not knowing anything about the overall task, but just at what point they have to switch from one task to another. And you can see that the system then converges to what we initially set out for them to do. And so this is just showing that you can do these kinds of things with real robot systems, actually no matter how many robots you have participating. Okay, so much for swarm methods from the swarm domain to solve the task assignment problem. I just want to talk about 2 more task assignment mechanisms so that you kind of get a broad overview of what's been done in the area. So there's one method called market-based coordination that maybe 10 or 15 years ago was extremely popular to solve the task allocation problem. And what it essentially does is it uses some ideas, or it's inspired by ideas from economics, essentially, where we're modeling the robots as self-interested agents that are participating in what we're calling a virtual economy, which is a collection of tasks, essentially. And here the tasks are commodities of measurable worth that can be traded. So the robots are trying to trade amongst each other which robot gets to do which task. And of course, you can apply this to most of the task assignment applications that I showed to you previously. So this particular image here is showing you something that corresponds to an exploration task or a surveillance task. So the underlying idea is that we have auctions that represent the actual assignment part of the problem. And we have an important component here, which is the auctioneer. So clearly these systems are, at least partially, they're centralized because an auctioneer functions by dealing with the bids that are made by the various robots that are participating in these systems. And there are different ways of actually implementing these systems. So the bids, they can be sealed bid versus open cry. So a robot can know about the bids of the other robots in the systems, or it can't. Then we can use first price auctions versus Vickrey auction, where you might be familiar with Vickrey auctions, where the sales price is the value of the second highest bid. And actually a lot of internet voting mechanisms actually work with Vickrey auctions. And then, well, we can do single item auctions where simply the highest bidder wins, or combinatorial auctions where we can then use underlying algorithms such as those provided by methods like the Hungarian algorithm, and multi-item auctions where a robot can win at most one item apiece, and the special case is actually the combinatorial auction for bundles of size 1. So what does this actually look like? Well, the system is the representation of the market-based system is in its most basic form is very, very simple, where we say, well, we have different tasks. So in this case, A and B. And we have a reward or a reservation price that we say that the task will allocate to the robot that actually solves this task. And then we have robots that essentially tell the auctioneer what their price is to solve these tasks. So essentially, what is the cost of a given robot to go and solve these tasks? So robot 1 here, for example, will have a cost of 50 to get to task A, and a cost of 100 to get to task B. And then same for robot 2, which has its own costs. And we can aggregate this cost information into this overall assignment or auction matrix, which allows us to view what would be actually happening in the system. So we see here, what's interesting is that robot 2 actually doesn't qualify to solve task A because the reserve price is not met, because robot 2 costs 130 in order to get to task A, but the reward is only 120. So a negative reward in this particular system is not allowed. So market-based mechanisms give you additional flexibility to decide or to define characteristics of the task-solving problem in this way. And the actual assignment algorithm, which is done by the auctioneer, is arbitrary, so you can choose whatever you want. You can use the Hungarian algorithm, or you can use greedy algorithms, and the complexity of your of the solution of the system will essentially depend on what assignment algorithm you use under the hood. So market-based allocation frameworks are essentially, or at least this is the way I view them, they're a wrapper framework around different assignment methods and different architectures by which you can actually communicate or implement communication mechanisms amongst robots and centralized elements in the system. So, and because of this flexibility, lots of different market-based mechanisms were proposed in the literature, especially in the early 2000s. And these are just a couple of references for you in case you're interested in having a look to see what different auction mechanisms were proposed. But in summary, basically, the flexibility allows you to define the cost estimates to be local or global. The cost estimates don't necessarily need to be batched, so you have a lot of flexibility in that. And these market-based frameworks can be decentralized to a certain extent. So who the auctioneer is up to the designer of these systems, right? So very flexible mechanism based on a couple of relatively loose rules. So I just want to go back and say a few things again about decentralized versus centralized assignment mechanisms, where the key thing here is when we have a centralized assignment mechanism, we need the cost estimates to be known at a central location, right? And the unit that is representing our centralized computational unit here, is able to perform these optimal assignments, but needs to be able to communicate with all the robots that are participating in your systems to tell them, well, this is what you're going to end up, this is what you have to do. So we not only need to be able to compute the cost estimates centrally, so to have a full estimate of the state of the full system, but also we need to be able to communicate with all the elements in our system. Where decentralized systems are much more relaxed, where you could be saying, well, the robots actually don't have global state knowledge of what the system overall is doing, and they have to negotiate who is going to be doing what simply by relying on local interactions with each other. So this is an interesting proposition if it's not possible to create centralized architectures, but clearly you're not going to get the same kind of performance. And of course, hybrid mechanisms can be defined that cross the boundaries between these two harsh or strict definitions of the architecture. And just to finish the lecture on the task assignment, I want to give you one example of a purely decentralized task assignment mechanism, because it's actually a quite elegant solution to this problem. And I just want to give you an intuition of how one would need to implement a fully decentralized task assignment algorithm if one would wish to do so. So in this particular system, what we need to do is to implement not only the control mechanism in a decentralized way, but also the estimation mechanism in a decentralized way. And so the way that Martinoli and colleagues went about this, so this particular piece of work that I'm showing to you is based on their paper, was actually very smart, because they said that a robot would be estimating a local stimulus that would tell it whether or not it should go and solve a given task. And the stimulus is something that it can compute completely locally, but has intrinsically, it's representing something about the global state of the system. So this has to be done somehow, because otherwise you're not solving a global task. And what was really elegant about it was, so they designed this experiment, which was the following. So here, what you see here in this image is robots that have grippers that can go and grab these poles, lift them, and move them to a different location in space. And the tasks that they wanted to solve was to say, well, all these robots together are going to grip these poles and put them into a row. Now, the perception that these robots have is essentially seeing a pole that is grippable, which essentially means that the pole has nothing to its left or nothing to its right-hand side, so that the robots can come down and actually grab the pole to lift it and take it to a new location in space. And so what was really smart about this paper was that the researchers said that the local stimulus is essentially going to be the time it takes for the robots to actually find a pole that is grippable, right? So you can already imagine what this meant for the system overall, because as these robots roam around, they take these poles and they place them into that line of poles that they're trying to create, and then they continue roaming around. And the more poles that are actually placed into this row of poles, the less poles the robots are going to be encountering. And so the stimulus was simply defined by saying, well, we have this threshold, which is going to be calibrated as a function of the time it takes for any robot to find a pole that it is able to pick up. And as this time starts increasing, the threshold starts going up and up, and the robots then eventually get beyond this threshold and say, well, I'm beyond my threshold now, I'm not able to find a pole within this time frame, and so I'm going to rest. And as you can see here in these panels, so here on the top-hand side, we have the average cluster size. So you're seeing that the number of poles that are placed in a row is growing as time increases. And here you see the average number of robots that are active throughout this task. So you see that as the cluster grows in size, the number of robots that decide that they should still be involved in this task assignment problem actually decreases. So this is done completely decentralized, in a completely decentralized way, because the stimulus that they're perceiving is local and a function of a self-calibrated estimate of the time it takes to actually solve the task. So this was an incredibly elegant way of solving the task assignment in a decentralized way. And so this is just to finish the lecture on task assignment, to give you an overview of the various methods that we can use and what guarantees they have. So we talked about Hungarian method, mean field approaches, market-based approaches and threshold-based approaches, and the overview just shows you what these methods do with respect to optimality, whether they're centralized or decentralized, and whether they're complete or not. So what are the guarantees that we can make that any task in the system will definitely be serviced or not? And I'll leave that for you to look at in the slides later. And my final slide will just includes a couple of pointers. The top bullet points are papers that I actually talked about, and these bottom bullet points here are actually a couple of problems that solve a few of the harder issues that I talked about during the lecture, which you can look at if you're interested to see what the problem definitions actually look like when we can't satisfy the various assumptions that we tend to make. Okay. So now we'll make a one minute pause whilst I just whip up the second bit of this lecture to talk about path planning.
Yes, so we can use this break, and if you have a question to the first part, you can ask. Yes.
Yeah.
Yeah. Hi, Amanda. Question, I misunderstood, but so what if we take estimate?
There you
so,
go.
yep.
There, yeah.
So you're always talking about giving estimates from agents to some centralized unit, or like having like decentralized market place estimations. But in every case, there was estimates for all agents, right? Like we need to collect estimates for all agents. So what if instead we had for each agent an estimate of himself and his, let's say, nearest agent?
Yeah.
So like, because I haven't noticed that. Okay.
Well, I mean, I think that's a good question, and this is perhaps one of the examples where you can implement a hybrid between centralized and decentralized allocation, where if within a local neighborhood, say I can talk to 5 people around me. Within this mini centralized system, we know what our costs are to solve certain tasks with respect to each other. And amongst us, we can potentially implement a centralized assignment mechanism for a subset of the tasks that need to be solved. And then at a higher order, you can then consider hierarchical compositions of these mini centralized type of assignment mechanisms to produce a system that ensures that you're actually assigning robots to all the tasks that you have in the system.
Yeah, okay, so we guarantee global optimal, right? And in that case, we will not guarantee it. So
no, you cannot, yeah.
That's the only, let's say, drawback, okay.
So there are ways of guaranteeing, you can actually try to solve systems in a centralized way with purely local interactions if you, for example, use a consensus algorithm, which is based purely on local interaction to retrieve local estimate, or to retrieve an estimate of the system state through local interaction. So this would be purely based on local communication, but you'd have to wait for the consensus algorithm to converge in order for you to have essentially an estimate of what the global state is of your system. And then again, you'd have to perform another consensus algorithm on the assignment, right? So there are ways of exploiting algorithms that solve global problems based only on local interaction, but they take much more time because you're waiting for the messages to propagate through the system and for agreement to be achieved.
One more question. May I ask something? What do you expect that could be the first real deployment of really fully decentralized swarming system? Like, where do you expect that such robots could be redeployed?
Well, there has already actually been some work published. So one example I can think of immediately is there was actually a science paper published early 2018 showing how we can deploy a swarm of drones flocking outside.
Sure. I know that there is a lot of already it's already not laboratory conditions, but still it's artificial problem usually. Or even if we are motivated by real application, still it's not a large deployment of such a system.
Yeah, I think it's a really good question. So if we think about, so one of my favorite examples is actually mobility on demand, where currently we have fully centralized systems, but there's a lot of potential, especially if we start moving to systems where the automakers are deploying protocols that allow cars to communicate with each other. We will see the beginning of a mix of centralized with decentralized systems where the cars are communicating information that is relevant with respect to neighborhoods, with respect to contextual information that is important for them to solve their tasks in the local geographic areas. And I think that has a lot of relevance for what we're trying to do, because this kind of decentralization is not only a simplification, but it also gives a lot of power, because you could imagine cars telling each other what the traffic conditions are in that local vicinity, which will allow them to refine potentially the cost estimates that were made by a centralized unit that is less accurate, right? So I think by combining centralized with decentralized, we can achieve even better performance than with a simply centralized system, which formerly we thought of being the optimal one. Yeah.
Yeah, I agree.
Okay.
Thank you. So please go ahead.
All right, so my last lecture, I want to give you a little bit of an overview of another topic that I find extremely important and relevant to the area of multi-robot systems, which is how do we actually do path planning and trajectory optimization in systems that are composed of not just one robot, but several robots. So what I'm going to start off with is, again, I will give you a bit of terminology that will allow you to talk about these problems, so a bit of a taxonomy of multi-robot path planning problems. And then I'm going to talk about two different approaches to the path planning problem, one in the discrete domain and one approach in the continuous domain. And at the end, I will give you one example of an alternative method that we can use to solve path planning in multi-robot systems, which is called basically the concurrent assignment and path planning problem. So those are the things that I'm going to talk about. But first, I'm actually going to start off by playing a movie, which I'm very fond of. And I just want you to have a look at this movie and see what's going on here. So this was actually filmed at EPFL in about 2012. And what you see here is a very large number of epoch robots performing navigation and multi-robot path planning. And so they formed the logo of EPFL. Now, this problem here is actually incredibly hard to solve, and I'm aware of maybe just one or two papers that have even attempted to solve this kind of problem. So what we're looking at here is so complicated because it's not only a collision avoidance problem, but every robot here has a very specific place within this logo that it has to occupy. So at the time that we did this movie, which is more than 10 years ago, we definitely did not have a solution to it. And so I'm actually wondering if anybody here has guessed how we actually were able to do this. Yeah, somebody there? Yeah, exactly. So what we did in order to produce this movie is we actually placed the robots into the logo position and we told them to disperse. And then we played this movie backwards. This is just showing you how difficult at the time it was to create these systems. And so we did this together with Francesco Mondada, who you might know, who is the creator of the epoch robot, all the other robotics faculty at EPFL, and I was actually one of the master's students at the time who was running around collecting the robots and putting them back into place. So, and I really like showing this movie because it really demonstrates on the one hand side, the difficulty of the problem, and then on the other hand side, how far we have actually gotten since we were considering these problems back then. Okay, so a little bit of terminology here. The first thing to consider is what domain are we going to consider in order to solve our multi-robot path planning problem? So what I mean by this is, well, we can perform our planning in the continuous domain. What this means is that we're essentially going to be creating time-parametrized trajectories in metric space to solve the path planning problem. Or we can solve it in the discrete domain, which essentially means that we're going to be solving the path planning problem on a graph where multiple agents are participating or are present on these networks, on these graph topologies. And of course, the graph can represent many different things. It can represent semantic space, or it can represent metric space through a discretization. Then goal assignment is very important, where we make the distinction between labeled problems and unlabeled problems. A labeled problem essentially says, well, we have a team of robots, and we know exactly which robot, so we have IDs, which robot has to go to which location in space. And an unlabeled problem says, well, I have specific locations in space that need to be occupied, but I don't care which robot goes there, right? So you could argue that the logo problem we had before can be solved through an unlabeled mechanism, where we just need a robot to occupy any given position in space. But not all applications can be solved in an unlabeled manner. So the problem representation can be either coupled or it can be decoupled. And this is another important distinction because it has a lot of implications for the complexity of the solutions that we find to be able to solve these problems. So in the coupled domain, we need to represent the state, the joint state of all the robots. So intuitively, what this means is that if I have 5 robots and they're solving a multi-robot path planning problem, I'm essentially representing this as one robot with 5 actuators, right? And this is the coupled way of thinking about a multi-robot path planning problem. In the decoupled way of thinking about it, we're going to say that each robot's state is represented independently. So we take account of every state of the robot without regarding the others. And then we're going to have to do some magic when the robots start colliding with each other, okay? So that's the kind of thing we run into when we model the problem in a decoupled way, okay? So the state space is different, the dependence conditions are different, and the complexity of the methods that solve these problems is also different as a consequence of these. And then finally, we have the planning domain, where we have algorithms that are either reactive, so based on dynamic observations, or that are deliberative, so classical planning mechanisms where we're trying to plan for optimality in a very explicit manner. And typically, these methods can only be solved through centralized and coupled mechanisms, whereas if we're looking at reactive planning algorithms, we can easily implement reactive mechanisms through decentralized architectures. And so this is how all these different terms you've been learning about start coming together. And finally, the computation itself can be performed in a centralized manner or in a decentralized manner with respect to any of these other methods that we looked at. Okay, so the first thing I want to introduce to you today is actually multi-agent path planning, which takes the multi-robot path planning problem into the discrete domain. Because I'd like to start with this because it gives you a very formal and clear representation of what the underlying problem is here. So what we do in order to be able to represent our problem within the multi-agent path planning domain is we do 2 things. We first say we have, or we're able to somehow discretize our environment. So one way of doing this is, for example, creating grids, regular grids that discretize our space. And the other thing we're going to say is that we have point robots. They don't necessarily need to be point robots, but we do need to have them be able to move into any adjacent grid cell, so up, down, left, or right. And so the problem that the multi-agent path planning domain tries to solve is, given that we have a number of agents at a specific set of start locations, and these agents have predefined goal locations, so we're considering a labeled problem here, in a known environment where we know where the obstacles are. The task is to find a collision-free path for all the robots in the system that optimize some higher order objective, okay? So that's the full multi-agent path planning problem. So as I mentioned before, we generally would assume that we have a labeled problem. So we have a specific robot that we want to reach a specific goal in this space. And this is a very natural way of formulating the problem because it represents many of the types of systems that fit naturally to this kind of representation. For example, automated warehouses, or any problem where you have a discretizable workspace with lots of obstacles for which you know their positions, okay? So what are the agents allowed to do? So I mentioned they're allowed to move in space, north, east, south, and west. And what they're not allowed to do is to create collisions. So we can think of vertex collisions, which consists of robots trying to move into the same cell, or edge collisions, which basically means they're not colliding in the vertex, but they're moving through each other, right? But what they are allowed to do is, within one time step, you can create a rotation of robots. If you have a constellation of vertices like that, and they're all just switching spots, that is something that is allowed, okay? So you see here that we have a underlying time discretization as well as a space discretization, and this time discretization is up to the designer to decide how long it actually physically takes for the robots to move from one grid cell to another. Common optimization metrics are make span and flow time. So make span considers the time of the last robot's arrival at its predefined location. So if you have a system of 100 robots, the make span will count, the timer will stop when your 100th robot reaches its goal. And the flow time is simply the sum of all the arrival times over all robots in your system. Or you can also take the average over that, it's equivalent. So those are the two main objectives that we're commonly interested in optimizing, and not necessarily at the same time. And I'll say a little bit more about that in a minute. So what does it mean now if we try to couple or decouple the system, and what is the impact of either one of these two mechanisms for the path planning problem? So if you look at these two graphics here, you can see a green robot and a blue robot, and they both have these predefined goal locations that they want to reach. And let's assume that we have a decoupled system where every robot plans individually in its own state space. And the green robot says, okay, I'm going to start moving and I'm going to go and reach my goal. And the result of that, if you don't consider a coupling of all the robot states and all their planned actions, is that once the green robot is sitting on its goal, the blue robot is not able to reach its goal anymore, ever, right? So what we mean, so formally, what this means is the completeness of the algorithm is not satisfied. And this is a very bad thing for problems that require completeness, right? So this would be an unacceptable solution for many real-world applications, as, for example, product dispatch in warehouses, right? Now, if you would model the system in a coupled manner, you would know that the green robot has to do this type of trajectory, the blue robot has to do that type of trajectory, and because it's a coupled state space, and you're treating it essentially as one robot with one higher order goal, the system knows, or the algorithm that you're going to use to solve this problem knows that the blue robot has to move before the green robot does. And that is one way you can achieve the completeness. So, and if you look at this, you'd think, well, if complete algorithms, if coupled algorithms achieve completeness, then why don't we just ditch the decoupled ones and we stick to the coupled algorithms? And that is exactly something I want to elucidate a little bit, because coupled path planning turns out to be very, very hard. So why is coupled path planning so hard? And we have to look a little bit at how these problems are actually formulated in order to get an intuition of the methods that we would end up having to use in order to solve these problems, and what the underlying complexities end up being. So in a coupled formulation, we start by saying that any robot I has a configuration space, C sub I. So in the case of grids, this is a very simple proposition, because we simply have the various vertices in the grid, and the robot can move from any vertex to another. But this configuration space can be viewed much more globally or generally, where you have kinematically constrained robots, etc. So once you start putting several robots together, the coupled path planning problem needs to model a joint state space. And what that means for this representation here is that my joint state space X is a Cartesian product of all the robots' individual configuration spaces, okay? So the dimensionality of X here grows linearly with the number of robots, right? So far, so good. We have a linear increase in the dimensionality of my state space. Now, what kind of algorithms solve the path planning problem for us? what we need to do is we need to find an algorithm, a classical search algorithm, that will solve this for us with completeness guarantees. One example is A star, for example. Now, what we need to do is we're trying to find out what the complexity is of trying to solve the coupled path planning problem. So what is the complexity of running an algorithm such as A star? So we know that A star requires time that is at least exponential with respect to the search space dimension, okay? So we know what the state space dimension is here, but we don't know what the search space dimension is yet in this coupled multi-robot path planning problem. So let's try and infer what the search space dimension is of this coupled path planning problem. And we can do this by thinking of, well, what is the state space for my coupled path planning problem, and how does that lead to an estimate of the search space dimension? So if we think of a system that is composed of 3 robots here, and you can't actually see the grids in the projection here, but you can imagine that there are grids there. We know that every robot has m possible states, which it can find itself in at any given point in time. And we have the Cartesian product of all these robots' individual configuration spaces. So at any point in time, we have m to the power of n states in a coupled system, okay? So, and this is modeling all the robots together, right? So m to the power n is the size of our joint configuration space for this coupled formulation of our multi-robot system. Now, what is the search space? Knowing that our configuration space considers m to the power of n states at any point in time, what is the search size of our A star algorithm? So we know that A star has a complexity that is in the order of the number of edges in the search graph. And for a sparse search graph, which we have in this case because we have an underlying grid representation, we know that this is roughly equal to the order of vertices in our search space. And so we know that the complexity of solving the coupled path planning problem for a state space of m states in any individual robot state space, and n robots is now owed to in the order of m to the power of n. And so the result of this is that the complexity of solving the coupled path planning problem is exponential in the number of robots, right? And the meaning of this is that we can only solve this in real time or with timing guarantees for very small robot systems. And that is why we commonly hardly ever use the coupled path planning algorithm to solve path planning problems for robot teams. So all of what I've told you before has been formalized in a couple of seminal papers. The first two actually were able to show formally that the coupled path planning problem is indeed NP hard in order to solve optimally was Laval and his colleagues in 2013. And this is considering either the make span or the flow time optimization objective. And what they also showed, which is actually very interesting, is that it is impossible to solve make span and flow time simultaneously. So when you're trying to solve these optimization problems, you have to choose either one or the other. And the optimal solution is going to be different as a function of which optimization objective you're trying to optimize for. And we know, however, that the coupled method is the only one that provides completeness as well as optimality, and we're trying to achieve this in many real-world applications, but it's really, really hard. And because of that, there's been a lot of attention devoted to this field, and there's been a proposition of many different methods. If you look at the papers coming out of Sven Koenig's lab or Max Likachev's lab or Howie Chausset's lab, you know that there are approximations to the standard coupled path planning algorithm that try to achieve the same performance, but with computational requirements that tend to be less restrictive. And they do this with some creative insights that allow this to become feasible. Okay, so much on that. I want to talk a little bit more about decoupled path planning. So even though we can find approximation algorithms to the coupled path planning problem, those as well have relatively high computational requirements. And wouldn't it be really great if we could actually find a way of implementing decoupled path planning so that it still leads to the desired performance? And one really interesting result was that we can actually achieve completeness in certain environments if we make certain assumptions on how the environment is actually built and how we place the robots and their goals inside these environments. And so there's this paper that was published not so long ago that says that if we define well-formed environments, then we can actually guarantee that any robot will be able to find or will be able to reach its goal location eventually, right? And the way it does this is by saying that the goals are distributed in such a way that any robot standing on a goal cannot completely prevent other robots from moving between any two other goals. So a very simple requirement that allows you to design an algorithm to create environments and to place starts and goals inside this environment so that you know that completeness will be feasible. So there are ways of getting around this. And so in this, just for a small example here, we can place starts and goals in this manner in an environment that looks this way. And we know that the paths here must have at least R clearance, where R is the space that a robot inhabits with respect to obstacles, and at least 2 R clearance with respect to any other endpoint. And the robot is then always able to find a collision-free trajectory to its goal by waiting for other robots to reach their goals and then follow their own path planned around those occupied goals, right? So here the interesting thing is that we're doing a decoupled algorithm and it's building on a prioritization metric, right? That allows you to decide which robot will go first. And the interesting thing about this well-formed environment is that any prioritization in this decoupled path planning method will allow you to achieve completeness. So let's have a look at the decoupled path planning problem in a little bit more detail. And I also want to talk a little bit more about how we actually can go about to design different prioritization objectives or metrics or rules that do different things for us, okay? So when we decide that we're decoupling our problem, what are we actually doing? So what we're saying is essentially any robot is basically planning their own trajectory in their own individual space-time, right? So they have a path that they're planning where in this planar domain we have X and Y, and the Z dimension here would be time. So every robot knows at which discretized time moment it will be occupying which cell in this planar domain. And when the robots then get within, say, communication range, so you can't see it here in the slide, but there's a disk around those 2 robots. They're communicating with each other. They're sharing their individual space-time graphs with each other, and they will then compare, okay, are these 2 robots occupying any 2 grid cells at the same moment in time? So a comparison is made. And if the comparison says, well, you guys are both deconflicted, so there's no overlap in your respective space-time graphs, then they can just carry on with their planned path plans. However, if they have a conflict, as in this particular scenario here, where at time step 1, they're both occupying this red grid cell, then they have to deconflict by creating a prioritization, okay? So this kind of prioritization can actually be done offline, so it can be done before any of the robots start to move, because they can all plan their paths, communicate with each other before they start moving. If you have some either fully connected topology or centralized computational unit, you can deconflict them, merge the path plans, create new path plans with a prioritization metric, recompute them, distribute these path plans, and then you're all set. Or you can do this in an ad hoc manner. Whenever the robots get into their communication range, they reconfigure their path plans. I like to show this graphic because it shows you visually what this might actually look like. So in this particular scenario, we're considering 2 robots. So imagine S1 here is a small robot that occupies that red kind of area. So S1 is the start of robot 1. And S2 is the start of a blue robot that occupies a larger area, so it's covering 4 vertices. And they both have to get to their respective goals, and in order to do that, they're going to have to cross over through this narrow corridor, okay? So in this particular system, we know that they cannot do this simultaneously because robot 2 requires a lot of space to move through this corridor. So what the robots do internally, the computation that they perform is they create this space-time graph and they try to figure out how they can get past each other so that they can each respectively find a way to get to their assigned goal locations. So in this example here, we are prioritizing the red robot, which you can see visually because you see that in the time graph, the red tunnel is moving across. It's already changing locations as time goes up, right? Where the blue robot's location is static as time goes up, so it's waiting for the red robot to go through the corridor. And once the red robot has cleared the corridor, the blue robot can start moving through the corridor and can achieve its goal. And so this is actually the optimal way of sending these robots to their goals for this particular system. And it's achieved by prioritizing the red robot versus the blue robot. So the key question here is how are we actually going to prioritize the robots? So ideally here, what we want to do is we want to consider all possible prioritizations, which the number for all possible prioritizations is n factorial. So this is easy to do if the prioritizations that you want to consider are amongst a very small robot size. So say you're only trying to do this once you run into other robots in real time. So say I only run into one other robot, n factorial for n equals 2 is not a big deal. But if you want to do this for larger communication topologies or larger networks of robots, it becomes intractable again. So because of this, a number of different prioritization heuristics have been proposed, and they all optimize a slightly different objective. So we can think of ideal path length. So maybe robots that have a very long path ahead of them should be prioritized because they should go first so that all the robots achieve a more or less reasonable time to get to their end goals. Or you could consider planning time. So if a robot spent a long time trying to figure out what path leads it to its goal, this might represent its difficulty of finding a feasible path plan, and hence that robot might need to be prioritized. Or workspace clutter. You could count the number of objects in a robot's environment to help you prioritize. Or something which we proposed actually very recently, which we're calling path prospects, which also prioritizes robots that have the least possible options to reach their goal locations. And so you can use these prioritization metrics to achieve complicated path planning problems. So this is one instantiation, so you don't see time represented here, but you could imagine this was a system where the blue squares were robots and they have different sizes and they all had to reach their goals, and you successfully achieved this by prioritizing the robots, and they deconflicted their path plans and they all reached their goals. Okay, so these particular papers here, I invite you to look at them at more detail to see how the prioritizations were done, but for time reasons, I won't be talking much more about how specifically the rules were implemented. So now I want to move into the continuous domain so that I can talk about the last few things I wanted to say with respect to multi-robot path planning. And again, so you've already seen this, a similar experiment here. And what you're seeing here is an example of multi-robot path planning in the continuous domain where the robots are not trying to achieve a formation, but they're actually all trying to achieve an end location whilst navigating around a very difficult situation that they run into in the middle of this experiment. So the robots have to get around each other at the center of this cross formation in a smooth and efficient way so that all of them reach their goals in, say, with an optimization objective that tries to minimize the time and also deviation from the straight line path to their goals. So what kind of methods can we implement that achieve this kind of behavior? So the first thing I want to talk about is a method or a module that allows you to do these kinds of things. So the Minkowski sum is actually something that allows you to implement a lot of the classical path planning algorithms in multi-robot systems literature. And this is just to give you an intuition of what the Minkowski sum actually does. So say that we have an area A, which contains, or actually the area A contains a set of position vectors that starts at this origin and ends anywhere within this blue area. And this area B contains essentially, you can think of B as an obstacle, right? And so if I do the Minkowski sum of this area A with this area B, This results in this light green shaded area, which is A plus B, that essentially is known as a dilation of the area B through area A, okay? So what's important here is you have to think of area A as really consisting of all the vectors that end up within the blue area and that start from the origin. And I'm going to show you how this is useful for the problem of multi-robot path planning. So what we want to do in the problem of multi-robot path planning is say we have a static obstacle that is this dark green area B, and we say we have a moving robot that is represented by this area minus A, right? What we want to do is we want to be able to say that if my robot is controlled through control point, through the vertex that is at the origin, then all I need to guarantee is that my control point is outside of the Minkowski sum of minus A plus B, okay? And you can see how this works out because minus A plus B is this light green shaded area, and I can now take the control point of my robot and move it anywhere that is outside this light green area, and you can see how the actual area of the robot, that is plus A, right, never coincides with the dark green area that B is occupying. And that's exactly what we want to achieve for obstacle avoidance. And so the Minkowski sum is a very elegant way of representing collision freeness or non-overlapping areas of robot bodies, okay? And that's the formal workhorse that we use in order to achieve this in the continuous domain, okay? So now I'm going to talk about a seminal method that was introduced in the late 90s that is called the velocity obstacle method, and is still to refer to today in many papers on continuous path planning in multi-robot systems. So the problem that we want to solve here is the problem of having two robots that have a given forwards velocity, and we want to answer the question, will robots A and B collide, given that we know what their velocity vectors are? And so this introduces what we call the velocity obstacle method, which basically says that if we look at this initial diagram here, and we assume if robot B were to remain static, right, and robot A is moving with velocity VA, the first thing I'm going to do is I'm going to compute the velocity obstacle of robot B with respect to robot A. And I do this by taking the Minkowski sum of minus A plus B, right? And this then shows me how if I were to move, if my velocity vector of robot A would point into anywhere within this cone. So the projector again is not showing it, but you can imagine that this cone here is in light gray. If the velocity vector of robot A were to be pointing into anywhere within that cone, eventually robot A would collide with robot B, right? So now what we need to do is we need to say, well, robot B is actually also moving. And so the simple extension of this is to say, okay, I'm now going to move this velocity obstacle by taking the position of robot A as the apex of this velocity obstacle, and I'm going to translate it by the velocity of robot B. And this gives me this new velocity obstacle of robot B with respect to A, which is this second cone here. And all I need to do now is to compute whether my vector of robot A is pointing into that velocity obstacle. And if it is, I know that eventually my two robots will collide. And so in order to avoid robot collision, all I need to do is to point that vector outside of the velocity obstacle for these two given velocities. And so this is a really elegant formalism because it simply allows me, given that I have two robot velocities, it allows me to say whether these two robots will collide or not. Okay. So now the question is, what am I going to do in order to avoid collisions? And this is the key question. So the way we solve this is by saying that we have a motion model for robot A, and we can compute a set of admissible accelerations, which then leads me to, so for example, let's assume that this gray box here represents the set of admissible accelerations that my robot A can do, given its dynamic constraints. And I know that I can compute a velocity vector by multiplying essentially my acceleration by a delta t, okay, by some discretized time element. then this would give me a resulting velocity of robot A at time t0 plus delta t, okay? So if I know what the permissible accelerations are of robot A, and I know what velocity vectors this results in, then I can simply go and say, okay, this is my velocity obstacle that I had previously. What acceleration do I need to perform that leads my robot outside of this velocity obstacle? And once I have found this new velocity direction for robot A that goes outside of, that leads to an area that is outside of this velocity obstacle, I know that I won't collide. And so that's the principal underlying concept of the velocity obstacle method. So there are a couple of details to it, which I will skip now due to time constraints, and just show you a couple of movies that show an implementation of the velocity obstacle method for multi-robot systems. So you can see that this is actually producing very similar behavior to the initial movie I showed to you before, with multiple robots trying to achieve goal locations. And so it's a very effective method. The important thing here to remember, and you will have noted this when I presented you the method, is that the robots, in order to actually perform this computation, they need to communicate with each other. They need to be able to tell each other what their current velocities are. And this is the fundamental underlying assumption of the velocity obstacle method. So if they don't know, if they cannot communicate with each other, or they don't know what their current velocities are without, if this is a very noisy estimate, then this type of method will not work well. So it's an important constraint to remember. Okay, and this is the very last thing I wanted to talk to you about today. And I like to present this because it's a completely alternative approach to the multi-robot path planning problem. And what's different about it is that we're going to be solving the assignment problem and the trajectory planning problem at the same time. And so the name for this problem is actually concurrent assignment and planning of trajectories. And the reason this is so interesting is because it alleviates the computational complexity of trying to find out which robot has to go where in an unlabeled problem, as well as generating the trajectories that lead the robot to their end goal. So the assumptions here that we're making in order for this to be able to work is, okay, so we have n robots, they need to reach goal locations. All we're going to pose for this system enabled to be able to work is that they have a minimum separation distance at their starts and their goal locations. And for this initial framework that I'm showing you today, we're going to assume that my robots are holonomic, okay? So that they can move along straight lines, and that they will all reach their goals simultaneously. So the problem is then, given that I have start and goal locations that are unlabeled, find the assignments and the trajectories, solve this simultaneously so that the collisions that I get are optimal, so that the trajectories that I then get are optimal with respect to an optimization objective and collision-free, okay? So the problem solves, by solving the concurrent assignment and trajectory planning problem, I get everything for free, essentially. Now, the key question here is, what is the optimization objective going to be? And that's a key design feature because that will determine whether or not I'm actually able to solve this problem effectively and elegantly with ideally not too much computational overhead. And so the really interesting insight that Turpin and colleagues made in their paper was that, well, I could consider an optimization objective which basically counts the sum of distances between all robots and their and potential goal locations, or I could consider the sum of distances squared. And what they were able to show, and that's really the interesting thing about this method, is that if I consider the sum of distances, then I can run into the situation where robots at halftime, so what you have to remember here is that all the robots reach their goals at the same time. This is one of the assumptions of the method. At halftime, if I use the sum of distances, the robots can actually be in a situation where they collide. However, if I use the sum of distances squared, then the assignments that pop out from this optimization problem is such that the robots are never colliding along their straight line paths, right? And so the analogy you can think of is if you have a stack of books and you use the sum of distances simply, it would basically, if you want to move one book from this end of books to the other end of the book, you would basically say, well, I'm going to take this book and I'm going to basically just lift it and put it onto the other side of my bookshelf, right? But the analogy of that example to this here is that you're essentially moving that book through all the other books, right? So you have multiple collisions there. If I were to solve the same shift of books, but considering the sum of squared analogy, it would essentially tell me, well, take each book and shift it over by 1, because that's what's minimal in terms of this cost metric. And if you take each book and just shift it over by 1, you get the same reconfiguration of your overall book set, right? Because you don't care about the IDs of the books, but none of the books are actually moving through each other, right? So that's the analogy of this sum of distances versus sum of distances squared optimization objective. Okay, so we then can go ahead and formalize the problem where we take the sum of the distances squared of our robot trajectories, and we minimize that. And the key result of this minimization problem is that if the separation distance between any start and goal location in this multi-robot system is larger than 2 times square root of 2 times r, where r is the size of a robot, then we guarantee that we will have collision-free trajectories. So the key thing here is that not only are we solving an underlying assignment, right? So what my D matrix is, so you'll recall that D is my cost matrix from the, say, Hungarian assignment algorithm. This is representing my sum of square distances between any robot initial location and any robot goal. All I have to do is solve this assignment problem and then let the robots run, because I know that they won't collide, because this optimization objective satisfies that intrinsically. So no trajectory path planning problem to be solved here, only an assignment problem. Given that, I know that the distance that separates any start and goal position is larger than 2 square root of 2. So this is a really elegant result because it solves a potentially very difficult problem in a very elegant way. And then you can use these kind of concurrent assignment and path planning problems for many different systems. And this is actually the very last thing I'm showing you today, which implements a version of CAPT for a reconfiguration of robots on a miniature highway. And before I play the movie, I just want to explain what's happening here. So what we want to do here in this miniature example is we have a platoon of cars coming from the back. And they want to reconfigure because they want to get around these 2 red robots here, which also have to reconfigure on the highway, so that they can let these three fast robots coming from the back get past, okay? So what we need to do here is solve 2 formation reassignment problems. And you can see how this is simultaneously an assignment problem as well as a trajectory generation problem, because we have to figure out which robot goes where in the new formation and how are the robots going to get to these new positions in these formations. And so these are the 2 formations that you want to achieve, right? You want the 2 red robots to achieve that new reconfiguration, and you want these 3 green robots there to achieve that new configuration. And I can run CAPT to solve this problem, so the robots communicate with each other, they assign their new positions, they reconfigure, and then they do what they want to do, which is get past the slow robots in this highway, and then they reconfigure again. So this is one practical example of how you can use a system such as CAPT to solve the concurrent assignment and trajectory planning problem in a very elegant and efficient way. And so to conclude, I again have a couple of pointers here for you. So very interesting book to read if you're interested in understanding planning in more depth is Stephen Laval's book on planning. So it's a very general and broad book about the planning problem, but highly recommended because it teaches you about classical notation in the domain. And then here are the papers about the different methods that I talked about, and a couple more recent methods that I also hinted on. So I hope I was able to give you a broad introduction to various domains in multi-robot systems. I'd like to thank you very much for your attention, also given the tremendous heat in this room. And I'd be more than happy to take any questions during lunch or this afternoon. I'll still be around. So thank you very much, and I wish you a great continuation.
Thank you, Amanda. Thank you very much for coming and for the great talk.
Oh.
I have a small present for you here.
Thank you very much. Lovely. Thank you very much. I appreciate it.
Yes, as Amanda said, we have we have lunch and coffee breaks for the questions. So right now I will tell you some important information, or I have two important informations and one super important. So regarding today's program, I have got some messages from you that some of you would like to change your group for the today's evening discussions. It's possible. So this is the groups A, B, C, and D, blah, 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 as you have in your benches. So just remember that A and B groups, the swarms, are quite overcrowded. So if you want to go to other letters, it's okay for us, but it means this is only for today. For tomorrow and the other days, please stay in your groups, because the second experimental exercise is already not related to this to the groups like swarms, formations, control, to these topics. So for today, you can choose other topic if you want. And also those of you who you didn't send us your preference, you can also choose these groups. So also for CTU students, if you like to attend discussions today evening, simply visit the rooms we will present. So this is the first thing. Then for the short presentations of students, we have 2 to 3 free slots. So if there is somebody who didn't send us abstract and title, still you can do it. So first 2, 3, maybe 4 students can be included into the list as well. And the last very important message is that we have lunch outdoor, of course, but we have also beer, because we want to show you like the best from Czech Republic, and it's quite common that we drink some beer with lunch, as in Italy or in France they drink wine, we drink beer. So you can try this behavior as well, and it's quite tricky to get the beer, because the beer outside, so this is also an opportunity for you to go out, because sun is there. So so grab some lunch, which is just outdoor, out of the lecture room, and then follow signs to find a beer. But please be in hurry a little bit, because we have maybe 30-35 minutes for lunch, and then please be here at 1 to see my presentation. Thank you.